Hello everyone. Today's lecture is about a very important topic in the context of microservices, resilience. We'll talk about how to make our system reliable and stable even when unexpected situations happen. In the world of microservices, we must admit that failures are inevitable. No system, even something as big as AWS, can guarantee 100% uptime or perfect speed for every single operation. But actually, what we can and should do is guarantee a high success rate for requests. And this is exactly where resilience comes to the front. Resilience means the ability of our system to keep working, respond properly to failures, and recover quickly after them. It is not about avoiding failures, it is about managing them effectively so that we can minimize their impact on users and business. Why do we need resilience? Failures are inevitable. We must be ready for problem and have strategies to handle them. Guarantee of availability. Resilience let us guarantee a certain level of success even if some operations fail temporarily. Fast detection and recovery. A failure is not the end of the world if we can detect, diagnose, and restore the system quickly. Business value. By keeping resilience high, we protect company reputation, prevent data loss, and financial damage. This helps the business continue working despite technical issues. Preparation for the unexpected situations. For example, chaos engineering allows us to test resilience by simulating failures. This way, we can find weak points before they become real production problems. It helps us prepare even for the rarest and most unexpected scenarios. Okay, resilience is a key idea in our microservices. In fact, it is made of four connected components: reliability, recoverability, adaptability, and observability. Reliability, this is the ability of the system to handle no types of failures correctly. For example, network call problem or issue with third-party services. With built-in mechanisms like retries, timeouts, and fallback logic, we can avoid critical consequences. Recoverability. This is how fast the system can return to a stable state after a failure. This time is measured from the moment of the failure to the moment the full functionality is back, not from when someone calls support. Here, effective monitoring is very important. Adaptability. This is the readiness of the system to react to new unexpected scenarios. It means our architecture patterns must be general enough to let the system adapt and continue working, even in rare or surprising cases. Observability. By the way, this is an extra aspect that makes resilience stronger. It is the ability to see the internal state of the system using metrics, logs, and traces. Without good visibility, we cannot detect problems quickly or respond to them correctly. Today, we will concentrate on the first three components, and about observability, we will talk in the next lecture. Now, to evaluate and ensure resilience in our systems, we need to monitor the key reliability indicators. They are the foundation for setting our goals and service level agreements. The first indicator is response time. This shows how fast the system processes requests. Actually, we usually do not talk about absolute numbers, but use percentiles. For example, the 95th percentiles means that 95 of requests must be finished in 1 second or faster. The next indicator is service availability. It measures how much time the service is working properly. Usually, this is measured in percentage like 99.9 availability. By the way, even big providers like AWS never guarantee 100%. For HTTP services, availability can be calculated as the ratio of successful requests, for example, with 200 status codes, to the total number of requests, including failures ones with 400 or 500 codes. And the third important indicator is data reliability. This tells us how often we can afford to lose data. In fact, it directly depends on backup frequency. For example, if backup runs once a day and an incident happens 1 hour before the next backup, we can lose up to 24 hours of data. So it is important to understand this risk clearly and set proper backup and recovery policies. All these indicators create the base for defining our SLEs, SLOs, and SLAs, which we will discuss next. Okay, to manage reliability and performance effectively, we use three concepts: SLE, SLO, and SLA. They form a clear hierarchy from measuring to setting goals and finally to legal agreements with clients. First, service level indicator. This is a measurable indicator that shows how the system works right now. For example, 95% of requests are faster than 1 second, or the service is available 99.95% of the time, or 500 errors are no more than 0.1%. This is the actual value. Next, service level objective. This is the target value for the indicator. We say we want it not to be more than this number. For example, if the SLE is response time, then the SLO is 95% of requests faster than 1 second. And finally, service level agreement. This is the legal agreement with the client where we promise to meet certain SLOs. If we fail, there are penalties or compensation. For example, the SLA may say service availability 99.9%. If it is lower, we return 10% of the monthly subscription price. So to sum up, SLA is what we measure, SLO is our goal, and SLA is the official agreement with the client based on these goals. By the way, once we move to microservice architecture, we start communicating through the network. And in most cases, the network becomes the source of problems in the system. Typical problems include the request may not reach the server at all. It is a direct communication failure. Then the server may be down or unavailable. For example, during a release when traffic switches to new infrastructure. The server may be overloaded. If CPU is near 100%, it may not be able to handle the request at that moment. The response may not come back to you. This is especially critical because the data may have been changed on the remote side, but you don't know about it. And finally, the response may be delayed. Okay, in our system, it is very important to have mechanism to identify problems and effective strategies to respond to them. To detect problems, we can use patterns like timeout and health check. To react to problems, we can use patterns like retry, bulkhead, and circuit breaker. So let's take a closer look at them. And the first pattern in our list is timeout. The idea is quite simple. If we send a request and do not get a response within a set time, we cancel it and treat it as failed. Why do we need this pattern? To prevent infinity waiting and resource blocking. Timeout stops a client or service from waiting forever. This avoids long occupation of resources like threads or network communication. To react faster to failures. Setting timeouts help the system respond more quickly and give feedbacks to users instead of keeping them waiting. And to prepare for retry. Timeout is often the first step before using the retry pattern. Okay, the health check pattern is about sending a simple request and getting a simple response. It helps us check that the service is alive, working, the process is running, and it is available. In fact, it does not require any complex logic on the server side. Let's look at the simplest example. It can be an HTTP GET request to that point like API/health, which return OK if the service is working. For a deeper check, a health check may include queries to dependent resources. For example, select one to the database just to confirm that it is available and ready to interact. Thanks to health check, we can monitor the system's health. And because it is so simple, it allows us to react very quickly if there is no response or if the service is not in the right state. Integration with orchestration and monitoring tools is also very important. Modern orchestrators like Kubernetes use health checks to monitor the state of pods and decide if traffic can be sent to them. Monitoring tools such as Datadog or Zabbix can also be configured to send HTTP requests to the health endpoint and check the response status. And even Jinx can be configured to track failure requests automatically. If a service does not respond or keeps returning errors for some time, for example, 3 failed requests in 5 seconds, Jinx can remove it from the pool of available servers for a while. So now let's move to how we can react to failures. And the first pattern in our release is retry. This pattern is used to handle temporary failures such as network issues, short downtime of the service, or other small problems that may be solved by sending the request again. Key policies for implementing retry. The first one, limited number of attempts. In fact, we must set a maximum number of retries to avoid endless loops and extra loads on the system. Interval between attempts. Here we have like fixed interval, simple but not always efficient. Exponential interval. This is the recommended approach. Early retries happens quickly and then the delays grow longer. This gives the recovering service more time to stabilize. Fibonacci interval. Similar to exponential, but the delay is calculated using the Fibonacci sequence. Random jitter. Actually, adding jitter to retry intervals is very important. It prevents many clients who fail at the same time from retrying all together and creating a new overload. Retry only when it makes sense. For example, if the client request itself is wrong, like a required field is empty, your trying will not help and will only waste resources. By the way, the retry pattern is already built into many libraries. It is a fundamental block for building resilient systems, especially when combined with timeouts. The next pattern is bulkhead. The name actually comes from ship terminology. Imagine a ship divided into several watertight compartments. If water enters one of them because of damage, the others stay dry, and the ship does not sink. In microservices, the principle is the same. A problem in one component should not sink the whole system. We isolate failures, so even if part of the services go down, the whole environment can keep working. The main idea is to separate clients or services into categories based on some parameters. For example, it can be their business importance, load level, or other criteria. For example, you can split users into premium and standard, or you can run more reliable servers for premium users or B2B clients with individual SLAs. In fact, it is common to create a separate production environment for a big B2B client, though that other users cannot affect it. So, let's look at the types of bulkhead isolation. Thread pool bulkhead. Separate threads are used for different tasks. If one group of tasks fails, it does not block the others. Service bulkhead. We run separate service instances, so one fail does not affect the rest. Database bulkhead. Databases or connections are split, so heavy load on one database does not slow down the others. Process or container bulkhead. Separate processes or containers are used to isolate failures at the infrastructure level. And the last one, the circuit breaker pattern, takes its idea from electricity. Imagine a short circuit in your home. The breaker opens the circuit to protect all your devices from damage. In microservices, the pattern does something similar. It prevents cascading failures by stopping new requests from going to a service that already has problems. The circuit breakers works like a proxy, watching the errors rate and switching between three main states. Closed. This is a normal state when the service works correctly. A request from the client goes through the circuit breaker to the server without limits. Open. If the circuit breaker detects too many errors, for example, the failure rate is above the threshold, it switches to open. In this state, all new requests are blocked and the client gets an error right away. This helps the broken service recover because it is no longer overloaded with calls. By the way, the client also gets immediate feedback instead of waiting for a timeout. And the last one, half open. After some time in open, usually after a timeout, the circuit breaker moves to half open. Here it allows a small number of test requests to reach the service. If they succeed, the state goes back to closed. If they fails again, it switches back to open. So the benefit of circuit breaker are clear. It gives faster recovery for services and instant feedback for clients, which improve the overall resilience of the system. So we just looked at patterns that help the system detect failures on time and isolate them so they do not bring the whole service down. But actually, even the best protection cannot guarantee that the global problems or big incidents will never happen. And this is where the next level comes in, disaster recovery. This is not about avoiding small failures anymore. It is about bringing the whole system back after a serious disaster. Disaster recovery is a set of practices that restore the system after a major failure or catastrophe. In this context, there are two key metrics. The first one, recovery point objective or RPO. This shows the maximum acceptable data loss measured from the last backup until the incident. For example, if we make backups once a day at midnight and an incident happens at 11 p.m., we may lose almost a full day of data. RPO tells us how much data loss we can accept. And the next one, recovery time objective or RTO. This is the maximum acceptable downtime from the failure until the system is fully back online. It is the time needed for the team to fix the problem and restore normal work. On the chart you see on the slide, these concepts are visualized. You can see the timeline with backup points, recovery points, the incident moment, the amount of lost data, and the recovery time needed to bring the system back. So we have already looked at the key metrics of disaster recovery, RPO and RTO. Now let's focus on the main strategies that help us reach these goals, balancing between cost and recovery speed. As you can see on the picture, there is a direct rule. The smaller RPO and RTO we want, the more expensive the strategy will be. The first one, backup and restore. This is the cheapest but also the slowest option. The idea is simple. You make regular backups of your data. In case of a disaster, you restore everything from zero using these backups. Recovery may take hours, so the RTO is high. The data loss depends on how often backups are created. This is the absolute minimum strategy. The next one, Pilot Light. This is more expensive, but recovery is faster. Here you keep critical components alive in a backup region or data center. For example, you may run a read replica of your database. Application servers are not running all the time, but starts only when the main system fails. This reduces RPO because data is almost up to date, and it lowers RTO because part of the infrastructure is already ready. Warm standby. This is even more expensive, but it keeps almost a full copy of your infrastructure in another region. The copy may have fewer resources, but it's already deployed and ready to run. Switching to it is much faster than Pilot Light because you don't wait for service to start. You can redirect traffic almost instantly. And the last one, multi-active active. This is the most expensive but also the most reliable option. It means having several identical copies of your production system running in parallel in different regions. The load balancer constantly spreads traffic between them. If one region fails, the load balancer stops sending requests there and other regions take over. This gives minimal RPO and RTO, but the cost is very high because you are duplicating your full infrastructure. It is important to know that these strategies should be chosen separately for each microservice, depending on how critical it is for the business. For example, for payment service where data loss is unacceptable, you may choose multi-active active. But for less critical services, pilot light or warm standby may be enough. Moving from recovery after failures, let's talk about chaos engineering, a methodology created by Netflix. Its main goal is proactive preparation for unknown failures and problems we may not even know about yet. Instead of waiting until these problems appear suddenly in production, we deliberately introduce controlled failures into our production environment with the help of special tools, often called monkeys. This allows us to observe how the system reacts and recovers, and also to find weak points. Let's look at some examples of these monkeys in chaos engineering. Latency monkey. This tool adds random delays into network communication. It helps us test system resilience to network problems. For example, when one microservice suddenly starts responding slower. Security monkey. This one runs penetration tests to detect security vulnerabilities in the system. Chaos Gorilla. This monkey can shut down entire regions or data centers, simulating large-scale disasters. For example, it may turn off a region in the US to check how the system in Europe handles extra load, even if this means higher latency for some users. Of course, this practice can be used in a staging environment, but usually it is done in production to get the most realistic feedback, though testing it on staging first is a good idea. Okay, today we talked about resilience, the stability and recoverability of our systems. The main idea is simple. Failures are inevitable, but the system must keep working and recover quickly. We highlighted four key components: reliability in predictable situations, fast recovery after a failure, adaptability to new and unexpected problems, and observability without which correct reaction is impossible. Then we looked at the main reliability indicators: response time, service availability, and data reliability. They form the base for SLE, SLO, and SLA, from a measured number to our target, and finally to the official agreement with clients. After that, we focus on typical network problems when a request does not arrive, the server is overloaded, or the response is lost. And here we use resilience patterns: timeout, health check, retries, bulkheads, and circuit breakers. They help us localize failures and stop them from breaking the whole system. We also study disaster recovery, global strategies for restoring systems after a catastrophe, from simple backups to full active copies across regions. It is always a balance between cost and recovery time. And finally, chaos engineering. This is when we deliberately create controlled failures to find weak spots before they appear in production. Here come the monkeys. They help us check if our system is truly ready for real chaos. So, resilience is not about avoiding failures, it is about being ready for them. To wrap things up, here is a quick knowledge quiz. Okay, we are done for today. Thanks a lot and catch you in the next lecture. Bye bye.